Okay, so, oh, you can't see it yet. Okay. Well, it's going to start up again. It was already on. Hopefully this won't take too long. Everyone have a good, Monday, good weekend. Oh, I should stand up here more. Got the microphone, I sound more official. So just a reminder too, our exam is next Tuesday, right? This Thursday will be, depending on how far I get into the last section of the P chapter, Thursday will be mostly a review of all the topics, and I'll try to talk to you about some exam studying strategies to help you out, and not make the weekend studying too terrible. Okay. Beautiful. So there she is. There's the quiz solution. So this first question, let me zoom in a little bit here. First question, just wanted you to determine the greatest common factor and factor it out. And just, that was it. That was all you had to do for that first question. Any questions on those? They were pretty straightforward, and most people got just about all the credit on those. All right, number 2 was factor these polynomials by grouping. So again, when you're doing grouping, it's all about looking to see if there's 4 terms. So clearly there are 4 terms. These ones you didn't even have to rearrange at all. So you just, factor the first 2, then factor the second 2 terms in the polynomial. You'll see that there's always going to be a common term, and then that one comes down, and then it's just whatever's left over. So this one's x squared plus 2, and then the second question was pretty much the same process. Well, not pretty much, it was the same process. All right, factor by grouping. Now, factor by grouping is important because we use that in other factor problems. So like in number 3, factor the following polynomials, right? So these are all, well, 2 of them are trinomials, the first and third one. So for the first one, this one's one of those easy ones because the coefficient in front of x squared is 1. So these first 2 terms in the 2 binomials, right? This is sort of reverse FOIL, right? We're trying to get to the state prior to actually FOILing out 2 binomials, are x and x. And then you just look at the last value here, 35, and look at the different factors of that number, such that you can get a sum or a difference of those 2 factors to be this middle term. So in this case, for 12, the factors of 35, 7, and 5 get you to 12. Now, because it's negative 12, we're basically adding up a negative 7 and a negative 5. So that's why there's negative signs in front of the 7 and 5. And then when you multiply the 2 negatives, you get a positive 35. I'll skip to number 3. So this one is another trinomial, but now I have a coefficient in front of the x squared. So you multiply 8 times 3, you get 24. You look at the factors. Now, the only factor that actually works in this problem is 12 and 2. So since we want negative 10x, we do negative 12 plus 2, and then we factor, we see the common term, and then we have our final answer from doing grouping. And now this middle one, again, anytime you only see 2 terms, look to see if you're able to take the square root of both those terms and get, a whole integer or, some x variable that has an integer exponent. So when I take the square root of 9x squared, I get 3x. And when I take the square root of 49, I get 7. So all you have to do is put the 7s on the end of the binomial, the 3x's in the beginning, and then put a negative and a plus, or plus negative. Doesn't matter the orientation of those signs. All right, so there, if you could see 2 terms, that's probably what you're going to do is the difference in squares. And then finally, this was the P5 question. Just like we did in class, you're going to go ahead and reduce each of these expressions to lowest terms and then specify the domain and then circle your answer. So here we have 2 polynomials, right? One's in the numerator, one's in the denominator. First step in these problems is to factor, okay? So these are the easy trinomial factors where you only have to worry about the factors of 15 and 12 respectively. So you'd factor them. You'd get these 2 binomials on either side of the fraction symbol, and you would see that you'd have an x minus 3 in both. Cross them off, you're good. So here's our reduced expression. So if I'm looking for the domain of that reduced expression, I only have to pay attention to the what could make this fraction undefined, right? And the only place it could be undefined is if in the denominator, if that was 0. So what value of x could make that 0? It would just be a positive 4. So your domain is all reals, meaning all real numbers can be plugged into this and get a real solution, except 4. Any other number, it works. And then the same process was for the second one. So again, I gave you a slightly more difficult trinomial in the numerator. Again, go through the process, you'd get it factored. And then there's another difference of squares in the denominator. You'd see that you'd have one term that cancels. So here's your final answer. So this is one where you'd have a fraction as the exception, right? So if you plugged in a -7/2, you'd get -7 plus 7 or 0. So again, all reals except -7/2 for the domain. Okay. We okay with all that? All right, perfect. All right, so that's quiz 2. Now, next order of business will be any questions you may have from section P5, which was the homework assignment that I gave you on Thursday. So this is, I have it on the screen already. This was page 58, 59, and I gave you those numbers. So is there any ones you'd like me to do? Yes, Bridget. 27. Let's check it out. All right, here we go. So again, I'm putting this at the end of the notes on section P5. And remember, you have access to these notes. So again, you could, if you're looking for more problems to practice, you could practice the ones I solved in class, and then you could actually just look at the solutions. All right, so here's 27. We have 2x plus 6. And I'm not trying to do like hashtag 27. That's like, we used to use it as like the number symbol, 15, 20 years ago. All right, so if you're wondering why I do that, that's because for me, in my head, that means number, not hashtag. 2x plus 6 over 4x minus 8. Now this is multiplying, so it's x squared plus x minus 6 all over x squared minus 9. Okay, so all of these problems, first step is you got to factor it. Okay, so let's quickly factor it. Hopefully we have that step down because we've been factoring quite a while. So I'm going to take out a 2 here and have x plus 3. And then take out a 4 and have x minus 2. And then I'm going to multiply that by, let's see, the numerator. It's one of those easy reverse FOILs. So the factors of 6 to get me a 1x is going to be a 3 and a 2. And I want the 3 to be positive and the 2 to be negative, right? Because 3x minus 2x gives me a positive x, and then the 6 is negative. And then we have a difference of squares in the denominator. Everyone okay with those factors, right? That looks good. All right, now, with these problems, when you're multiplying rational expressions, this is what I did in a couple examples. I said, all right, well, when you're multiplying, you're just multiplying the numerator and then multiplying the denominator. So I just was putting a line here to signify, all right, well, now we just have this big fraction. And really, so 2 times x plus 3 is also being multiplied by x plus 3 and x minus 2. Now, once we have this, we just have to cancel like terms, right? So if you had like xy over 2y, right? Couldn't you cancel out those y's, right? Well, just like canceling out single variables, you can cancel out common binomial terms. Now, this is a good example because in the numerator, there's 2 x plus 3 binomials, but there's only 1 in the denominator, right? So you can only cancel out 1 from each. So I'll cancel this one out, and just because this one's here, I'll cancel that one out. The only thing left to cancel, well, let's see, there's 2 things we can do. We're going to do x minus 2 and x minus 2. And let's see, what's left? We only have those integers, right? So if I just had 2 over 4 by itself, couldn't I do that and get 1/2, right? So you could do the same thing here. We're going to end up getting a 1/2 from that 2 over 4. Okay, so what's my final answer going to look like? Well, the only thing I have in the numerator is x plus 3. Now, in the denominator, and this came up in a question in one of the Zoom office hours I had, the question was, well, can I put this 2, over here next to the x minus 3? And the answer is absolutely yes. Like if you had x times y times z, that's the same thing as z times x times y, right? It doesn't matter the order in which you multiply, okay? So you could put that 2 right next to the x minus 3. Now this one, you might be thinking, well, should I distribute that 2 in the denominator? I would say no. I would say try to leave, because it'll be just less work when you're doing an exam. Just leave it in factored form, okay? So does that make sense? All right, anything else from this section? Yes, sir.
Go over the number 79.
I absolutely can. So hashtag 79. What do we got over here? Let's see. All right. So we have, this is a good one. And by good, I mean there's just 3 rational expressions. So I'll take this one step by step because this sort of sums up all the different things we had to do for adding or subtracting rational expressions. Oh, 77. Oh, this is not a bad one either, but you want to do 77 instead?
Yeah,
No, that's okay. Well, you know what I'll do, just in case anyone wanted that one, I'll come back to it. 77. So this is x minus 3 over x squared minus 25, and then we're going to subtract this expression. Awesome. Okay, so again, let's factor everything. So we have x minus 3, and then we have a difference of squares, right, in the denominator. It'd be x minus 5, x plus 5. Can't do anything with the x minus 3 in the numerator just yet. So we'll factor this guy here. This one's a pretty simple one, right? X's are there, and then the factors of 20, that could give you a positive 9. They're going to be 5 and 4, and then we'll make them both positive. It'll be 5x and 4x is 9x. Okay, so we're fully factored. Now, the rule for this one is like if you had a over b plus, I believe I use c over d, right? You want to combine 2 rational expressions. You could just do this. It's a times d plus b times c, and this could be plus or minus, by the way. It doesn't matter which one you use, over b times d, okay? You could absolutely do that in this problem, right? And I think that's the way I showed you in the notes. Just here's another way to think about it too. You can find something called the LCD. That's the least, this is probably, well, this is definitely how the book does it, least common denominator, all right? Now, if I wanted to put that in layman's terms, it's just you need to include all of the possible terms that could show up in either denominator. So like as an example, x minus 5 is in one of them. So that has to be in the least common denominator. X plus 5, well, that's in both already, so that's good. And x plus 4, that has to show up also in the denominator. So here's what I'm going to do. I'm going to do it with this LCD way, just so you have a couple different examples. So what's my common denominator going to be? Well, I know I have to have an x minus 5, okay? I know I have to have an x plus 5, and I know I have to have an x plus 4, all right? Has to be there. That's the least common denominator. Now, what do I have to do now? So let's look at this first term. Out of what I'm just putting a little line under, and then this common denominator, what's missing between what I just underlined and then this least common denominator on the bottom? X plus 4. So that's what you multiply x minus 3 by. All right, you multiply the numerator by whatever the original fraction was missing compared to the least common denominator. This will actually save you factoring in the long run if you can do it in this way. Right, because if you were to pull this out, right, if you were to now just reduce this, you could cross off, right, the x plus 4s, and you still have the original rational expression. All right, so good. So you keep the minus sign. All right, so now I'm going to put some brackets here because we're going to have a trinomial or two binomials. What's missing from the second rational expression in my least common denominator? It looks like the, which one? Which binomial? X minus 5. All right, now, so now you're done in the denominator. You've already determined the least common denominator. Now you have to go ahead and multiply some stuff out up here, okay? Or, I mean, you could factor out the x minus 3 if you'd like. Should we do that? You know what, let's do that just for fun. Do you see that I have two terms here, right? The x minus 3, x plus 4, that's one, right? One term in the numerator, and then it's separated by a negative sign. So I'm going to factor out an x minus 3, because look, if you could leave it in factored form, that's probably better. And let's see what we have left over. So I'll use square brackets. So if I factor out x minus 3, I'd have to multiply by x plus 4, I should get that first term, and then subtract. You see that I'd have to subtract x minus 5. Yeah, this is going to make this nice and easy. So what do you get inside those big square brackets? Well, do you see the x's are going to cancel? Right, because you'll have x minus x, poof, that's gone. And then you're going to have 4 minus a minus 5, which is 4 plus 5, or a 9. So the only thing, so this thing really simplifies to a 9. So now my fully factored final answer is 9 times x minus 3 all over x minus 5, x plus 5, x plus 4. Look at that. So that was pretty easy. Not too bad. All right, so it's all about finding, look at these denominators here, and if there's something that's, really you have to include everything that's there, right? But you don't have to, like for these x plus 5s, you don't have to put x plus 5 squared in there because you only need one of them. It's the least common denominator, so it's the least amount of terms. Okay? Any other questions about, yes sir? 23. Okay, so we have okay, so this is we have to reduce this rational expression. Okay, so these are trinomials, but you can't do that trick where you multiply the first coefficient by that last coefficient, right? Because that only works for when you have a quadratic equation, meaning you have well, it'd actually be even polynomials, but even degree polynomials, but we're only going to worry about quadratic. So this is not a quadratic, right? This has higher powers. So what you want to do is just find the greatest common factor of the numerator and then take it out, and then do the same thing to the denominator. So what's our greatest common factor here? It's probably the integer is a 2, right? 2 divides everything, and then x squared, right? So we have a 2x squared, and let's see what else we can get here. So it's going to be a 3x squared plus 7x plus 2, all right? And then we'll do the same process for the numerator. So again, it looks like 2x squared, and then we'll be left with a 3x squared minus 7x, or no, minus 5x, sorry, and then minus 2, okay? So right off the bat, what can I do with those 2x squareds hanging out in the front? Yeah, if you see two terms there and they're just sitting there and it's all just being multiplied like that, get rid of them. Boom, they're gone. Now they're not gone and leaving nothing behind. They're just leaving ones behind, okay? So in this problem, you also have to consider, can I factor the rest? So let's look at this first one. I'll just put an arrow over here, right? So this looks like I could do 3 times 2 and get 6. All right, so the factors of 6. 6 times 1, 3 times 2. Can I get 7 from that? It looks like I can, right? So it would be, again, I'm going to 3x squared. The first term is the same, and then I'm going to do plus 6x plus x plus 2. So then I take out a 3x. So now I'm factored by grouping. It'll be x plus 2 plus 1 times x plus 2. All right, so now I know the numerator is going to be 3x plus 1, right? That's what was left over here, times x plus 2. And now we're going to do the same thing to the numerator. Again, 3 times 2 is 6. Again, the same factors, 6 and 1, 3 and 2. How do we get 5? I think we're going to use 6 and 1 again. Yeah, we're going to use 6 and 1. So it's going to be 3x squared. And then I'm going to do minus 6x and then plus x minus 2. And then let's see what happens. We're taking out a 3x. And then I get x minus 2 plus 1 times x minus 2. So I know my fully factored trinomial is going to be 3x plus 1 over x or times x minus 2. And then look, we have a binomial that could be canceled. Again, they're gone. So all I'm left with is x plus 2 over x minus 2. So that big ugly thing at the top is reduced to that. Yes?
Why couldn't you use 3 and 2?
So in this one, let's see what would have happened, right? Oh, well, actually, you could just think about it in this way. 3 and 2. So in order to get 5, I'd have to add them, right? But not only that, I'd also have to add them negatively. Does that make sense?
Yeah.
So here's what would happen. If I had, let's say, well, I'll just show you why it doesn't work. So 3x squared, we'll do minus 3x minus 2x, because that's the only possibility, right, to get the negative 5x. And then it's what? Plus or minus 2. So let's see. You get, I'm taking out a 3x, and I get x minus 1. And then I get minus 2. Here it is. If I take out a minus 2 here, I'm going to be left with an x plus 1. Do you see that these two terms aren't going to work? Okay. So if you ever get to that point, it's not going to work. You have to try the other factor. So both of these look like they can give you the 5x that you need, but only one of them is going to work in this particular problem. Some problems it doesn't matter. I think the problems that end in a negative number, like this negative 2, one of them is only going to work. Okay. All right, I'll take just one more question from this section if anyone has it. Okay. Now, I noticed about, I think it was 16 of you submitted the homework. So I don't know if just some people forgot. And again, you're submitting as much as you can do. If you can't do it all, I'm not penalizing you, but like instead of giving you +2, if you gave a good effort, I'll give you +1. You know, any type of points are good. So I'm going to give you to about, noon today. So if you still have to submit the homework and didn't, go ahead and do that and put it in the Dropbox. All right, so P5 is done. So let's move right along and continue in P6. And I'll kind of review what we've done so far. And this is the last P section. Last section for the exam next Tuesday. All right, so the first thing that we talked about, so the title is Rational Exponents and Radicals. We just talked a little bit about square roots, something, prior information you've had. Just wanted to make sure you understood what the symbol was called. It's a radical symbol. And when you take the square root of a number, there's always a principal root. But that doesn't mean that's the only root that would give you the correct answer. So the square root of 16, right? Couldn't you also get -4? So a lot of the times when you take the square root of 16, right, you really should be saying plus or minus 4, right? Because you could square -4 and still get a positive 16. So just keep that in mind. All right, so then we define that a little bit more technically. And again, we kind of just went down there and talked about that as well. And if you square a square root, you just get the thing underneath the radical, which is called the radicand. Okay. So the first type of problem in section P6, it would just be finding square roots of ratios. So these are pretty straightforward. You'd be given something like, I'm going to give you a little, just slightly more difficult example, just so you could see. Actually, I can't in this section. Just forget it, because that's going to be down here. All right, so these are easy. If you take the square root of things that you can take the square root of, you just get the solution. So like square root of 81 over 49, square root of 81 is 9, square root of 49 is 7, boom, you're done. Then we talked about these rules. This is what I was getting at. If you have two numbers being multiplied together under a square root symbol, you can separate those numbers out into their own square root symbols and then do, whatever type of math you'd like to do. And then you could do the same thing with ratios. You could separate them. So you could take the square root of the numerator separately from taking the square root of the denominator. And I'll say again that this warning, a lot of people think you could do this, but you cannot. Okay? All right, here were a couple examples. So I went through those. I don't think I did every single one. So let's just practice one here just to make sure we understand what's going on. Let's just do a simple one. Let's do... All right, so let's say we have the square root of 72x to the fifth. So first thing I would probably do is separate these two things. Let's worry about the integers by themselves, and then let's worry about the x terms or y terms or whatever you're working with in the problem. All right, so now that's supposed to be 72, sorry. So now when you're working with these numbers that you can't directly take a square root of, can you find any factors of those numbers that are easy that you could take the square root of? So think about 72. What are some factors of 72? Yeah. 9 and 8, right? But could you split 8 up even more? All right, but let's do, just think, say you saw this on a thing and that's what immediately you would do. Let's do it. Square root of 9, square root of 8, we'll put that as that first step. And then how about x to the fifth? Now, square roots are easy. You could always take the square root of powers that are even, right? So are you okay with this? Could I split this up to look like this? The square root of x to the fourth times the square root of x. That's doable, right? Okay. So let's see what the next line would be. So evaluate the easy square roots you see. So it's 3 for the square root of 9. But what about the square root of 8? Is there a factor of 8? Well, it'd be 4 and 2, right? Is that what you're going to say? So this would be the square root of 4 times the square root of 2. And let's see, times, so what's the square root of x to the fourth? Well, it's just x squared. And then you have to leave the square root of x. So now it's 3 times the square root of 4, which is really a 2. So 3 times 2 is 6. So we have 6 square root of 2 times x squared square root of x. Now, we don't want to leave that as the final answer. What we'll want to do is every term that's not under that radical symbol, so this would be the 6 and the x squared, you're going to put them together, and then everything that's under the same square root symbol, so the 2 is under a square root and then the x is under a square root, you can put them together back under the square root. Okay, so that would be our final answer there. So Bridget, just why I was hesitated when you said that, you could have just went right for 36 and 2 and took in the square root of 36 and got 6. But as long as you noticed that you could split up the 8, you would have been fine. You got the same answer. Okay? Beautiful. And you could do the same sort of thing with quotients and just cancel some things out. All right, so we've covered that. Now, here is the next part. So this is the newest stuff from this section. So we're just going to term this other roots. And this is a lot of writing because I'm sort of, there's a nice table in the book, but I'm just going to try to make it as short as I can. So if you have some integer a and it's greater than 0, all right, it's possible to take the root of some number, a, that's not a square root, but it could be the nth root. You could take a cubic root, for example, a root that has a 3 up there, and that could be equal to b. So that's the same, instead of, like, for the square root, right, I'll just put this as a reminder up here. The square root is, there's really a 2 up there, right? We just don't write it there. So if I had the square root of a equals b, that means b squared is going to be equal to a. Well, when you have the nth root, you don't know, you could put any integer there. We just know that b to the n is going to be equal to a. Okay. Just give you an easy example. Let's say you had the cube root of 8, right? So you want to ask yourself, what number would I have to raise to the third power, right? So essentially I'm looking for b here. So b to the third is equal to 8. So what number is b? 2. So the answer to this is 2. Right, so square roots are easy to think about because you've been working with them for a long time, right? 25 squared, or 25 is 5 squared. Now you just have to start thinking about cubes. Just, I'll let you know right now, I'm not going to have you worry about any other types of crazy radicals except to the third power. So you will have to know some of those, like 4 cubed. And again, it's just 4 times 4 times 4. So, and I won't kill you with the types of numbers. They'll all be doable. Okay, now there's just a couple things now. If, let's say a, the thing underneath the square root, is less than 0, right? And n is odd. All right. Now, what does that look like? Well, how about this? If I had the cube root of -8, what's the answer to that? Could I take a cubic root? I can, right?
-2.
Yeah, so odd roots, you're allowed to have negative numbers in there to get real solutions, right? Because if you did -2 cubed, right, that's -2 times -2 times -2, right? So only one pair of negative signs cancel out to be positive, so there's still one left and you get -8. So just be aware of that. For odd ends, you can have roots. Now, again, if a is less than 0, but n is even, right? All we're going to do for right now is say something like the square root of -8. All we're going to do is say it's not a real number. Later on in the book, we'll work with these types of radicals, which give us something called complex numbers. But for right now, we're not concerned with complex numbers. And if you ever see it, the last thing would be, if a is 0, right? Can you do that? Can you take the square root of 0 or the nth root of a 0? Yeah, it turns out you can. So it's just 0. Okay, so that's pretty simple. All right, is there anything else on this page? All right, so let's just look at a couple examples. Again, I'm not going to give you too many crazy ones here because I'm trying to think ahead to how you're going to apply this, and you're not going to have too many things. So how about the cube root of -27? Because that one will come up a lot. So what do you have to cube to get 27? Remember, they all have to be integers. What do you think? Yeah. Yep, this one's going to be -3 because we have a negative underneath there. Let's see. Again, I want you to have a couple of them. How about the cube root of 81? Actually, is that right? I don't know. I don't know why. But I think I was thinking. Let's see. This is going to be. What is that going to be? Sorry, it should be that. I haven't mistaken my notes, and I just realized it. That's a tough one. 729, right?
Is it 9?
It's 9, right? Because 9 times 9 is 81, and then 81 times 9 is 729. Okay. And again, if you had something like the cube root of 27 over 64, you could separate those. So you had the cube root of 27 in the numerator, the cube root of 64 in the denominator. Now we know the cube root of 27 is 3. How about 64? That's a common one you'll see. So that's going to be 4 times 4 times 4. So it's 3/4. All right, pretty simple. All right, how about something like this? We have the cube root of negative 8 x to the 6th. So just like these previous ones, I'm going to break up the integers and the variables. So I have the cube root of negative 8 times the cube root of x to the 6th. So what's the cube root of negative 8? We already did it. It's negative 2. And how about the cube root of x to the 6th? So this is saying, basically, what do I multiply together 3 times with the x variable to get x to the 6th? So I need to do this. Now, I want to know what exponent here will allow me to get an x to the 6th. Now, this trips some people up sometimes because it's 2, right? Because when you multiply variables, right, what do you do to their exponents? You add them, okay? So in this case, I was able to do 6 divided by 3, really, and that worked out. So then that answer is going to be x squared. So it's negative 2x squared for that problem. All right, so you're not going to see anything crazier than a cube root when we're talking about that. Okay. Okay, the next thing. Are we okay with this? Again, everything I've done so far has been the same type of problem. I've just been giving you a bunch of rules, okay? Same type of problem, though. All right, here's a new type of problem, and I'm gonna term it like radicals. And all that means is it's radicals with, oh, that's terrible, with the same n value. And what do I mean by n value? I mean the square root of n. All right, so with the same, they have to be the same type of root. Either they're all square roots, they're all cube roots, that sort of thing. Okay, so what do I mean by this? Well, here's how you could do a problem with like radicals. Let's say you had this. This is a real simple one. Okay. So immediately you might think, well, what the hell can I do with that? That's crazy, right? Well, that is equivalent mathematically in terms of the process to get to the next step as this. 7x minus x. Right? What's 7x minus x? It'd just be 6x, right? That's simple. That's exactly how you have to think of doing these types of problems. When you have a like radical, like this, pretend that they're just variables, as long as they're the same. So my answer for 7 square root of 2 minus square root of 2 is going to be 6 square root of 2. Just pretend the like radical is a variable. Okay? Very easy, I think. I just pretend they're like radicals. Now, how could these problems get a little bit more difficult would be if I gave you something like this. Let's say the square root of 45x plus the square root of 20x. All right, do you see a like radical?
Yeah.
No, I don't see them, right? Because like the thing inside the radical has to be the same as well, right? But here's what you do. Can I simplify these two terms a little bit? All right, so that's the first step. If you look at the two radicals or whatever you're adding or subtracting, and you can't immediately add or subtract, The first step is to, like anything else, we're going to simplify. All right, so let's start with the 45x. Here's how I would split that up. I would do the square root of 9 times the square root of 5 times the square root of x. Okay, that'd be, I'll just do that on that line. And now I'm going to go over to the 20x. I'm going to do the square root of 4 times the square root of 5 times the square root of x. Okay, so what do we have here? Well, the next line will be 3 times, now the 5 and the x are both under a square root, so I could just put them there. So 3 square root of 5x plus 2 square root of 5x. Now do we have a like radical? Yep, like radical is the square root of 5x. So now all you do, pretend they're variables by themselves, and now you just add the coefficients in front of them. So the final answer here is just going to be 3 plus 2, or 5 square root of 5x. Okay, I'm going to give you a couple of these. Let's do a cube root example. All right, so there we go. So the cube root of 54 plus cube root of 16. They're not like radicals yet. We have the same root, the 3, but then the thing inside has to be the same, which they're not. So we have to start splitting them up. Now, typically, well, not typically, in these problems, if you simplify each expression down to its simplest form, that's where the like radical is going to appear. All right, so let's look at the square root of 54. How could I split that up? Again, you're thinking about numbers being raised to a power. Now, you can't do the cube root of 54, right? So what are some factors to 54 that have cube roots? Well, what's half of 54? Is that 27? Like 27 times 2? Hey, I could take the cube root of 27, right? So I'm going to split this up into the cube root of 27 times the cube root of 2. All right, that one's done. Now how about 16? Is there a factor of 16 that's a cube root? 8, right? We could do that one. The cube root of 8 times the cube root of 2. All right. Simplify these. So now the cube root of 27 is 3. So we have 3 cube root of 2 plus, and then the cube root of 8 is 2, cube root of 2. So now we have cube root of 2's as our like radical. Pretend they're variables. So I just add the exponent, or add the coefficients. So 3 plus 2 is 5, and I get 5 cube root of 2. Yeah, pretty good. Not too bad. So it's all about simplifying them and then finding that like radical. Okay. All right. Any questions on those? Excellent. The next topic. And again, these are all topics that, you're going to need later on at some point. Maybe not necessarily here in this class, but somewhere else. All right. The next one is, and I don't think these are too bad either, rationalizing rational expressions. Okay, what does this mean? Well, this just means removing radicals from either the numerator or denominator. Now, which one do you have to remove? Well, sometimes you'll have radicals in both, but the problem instructions will tell you to rationalize the numerator or the denominator, right? So it'll be crystal clear which one you're supposed to do. So let's start with a real basic one. We'll start with rationalizing the denominator. So our goal is denominator. Our goal is to get rid of the radical in the denominator. So let's say we have 10 over the square root of 5, right? I don't want that square root down there. I don't like it. Okay? So what do I do? Well, in all of these problems, okay, our only choice, because we don't want to change the fraction or the rational expression. All we want to do is multiply it by something that doesn't change the original thing. And what does that mean? Yeah. Okay, so you're basically saying you're one step ahead of me, but that's okay. You're going to multiply by 1, right? If you multiply anything by 1, it doesn't change the thing. So instead of 1, what she's saying is, let's do the square root of 5 over the square root of 5. Is that what you're saying? Yeah. So when you do that, I'm just multiplying by 1 because you could cancel those square root of 5s, but I'm not going to cancel them. And now you just like those other problems where you're multiplying rational expressions, multiply across the numerator and across the denominator. So the numerator becomes 10 square root of 5. And then what's the square root of 5 times the square root of 5? Well, it's the square root of 25, right? So just as an aside, if you do square root of x, just as a reminder, times the square root of x, you get x, right? So that's the principle of doing this rationalization. So the square root of 5 times the square root of 5 in that denominator just gives you a 5. Now the problem's almost done because you have to then simplify the result. So I could cancel the 5 on the bottom and then divide the 10 by a 5 and get a 2. So my final answer is 2 square root of 5. Now, not every time will you get rid of it, will change from a fraction to a non-fraction. That won't always happen. It just happened to happen in this one. Okay? Let's try another one. Okay, what do I multiply that one by? And again, you just look in the denominator, and we're going to do the square root of 8 over the square root of 8. So in the numerator, we have negative 3 square root of 8 over 8. Now, I'm almost done. What do I have left? What's left to do? Remember, we're trying to simplify to lowest terms. What can I do with that square root of 8? Can I split that into a square root of 4 and a square root of 2? So beware of that. So now I have negative 3 times the square root of 4, which is just 2. So that's a negative 6 square root of 2 over 8. And then I simplify that. So I can divide 6 and 8 by 2 and be left with 3 and a 4. So now my final answer is negative 3 square root of 2 over 4. So there's an example where the fraction remained, and that's absolutely fine. Okay. All right. So they're easy. You just give you a little fraction, you figure out what's the denominator, and you multiply across and simplify. How about something like this, though? What about this? What about something like this? What if I wanted to rationalize the denominator there? What do you think? You ever done that before? Yeah, what do you think, Kelly? Okay, you're absolutely right. Because again, I'm still multiplying by 1. Do you know what that's called? Because it's not the same, right? You have square root of 5 plus 2x, but square root of 5 minus 2x. What's it called? I couldn't hear you. What's that?
Reciprocal?
Not the reciprocal. Close, though. It's a long name like that. Have you heard of conjugate before? Okay. It's the conjugate of a binomial. All that means is it's the same binomial with the sign in the middle switched. That's it. So these are also not too bad. Now, the only thing you have to do is you have to FOIL, right? Because we're going to be multiplying across again. So you're going to be FOILing things that have square roots. But let's just work through it. So look at the numerator. That's going to be easy for right now. That's just square root of 5 minus 2x. It won't always be that easy because you won't always have that 1 up there. All right, so let's do this FOIL. So FOIL is first. So square root of 5 times 5 is 5. That's good. Now you have the FOIL is outer. So square root of 5 times negative 2x. So minus 2x square root of 5. Now we'll do inner. And then 2x times square root of 5. So plus 2x square root of 5. And then finally the last 2x times negative 2x, or minus 4x squared. Okay. So the reason we did like radicals is, do you see that you have to look at like radicals here? But what happens to these middle terms? Yeah, they're gone. They add up to 0. So now your final answer is the square root of 5 minus 2x all over 5 minus 4x squared. So were we successful in rationalizing the denominator? Yes, we were, right? There are no radicals in the denominator anymore. Now, is it okay that the radical ended up showing up in the numerator? Absolutely fine. Okay? Good. All right, let's do another one. Yes, sir.
We have to like reduce
Good question. So you're asking about this right here?
Yeah.
Okay, because there's a negative sign between two different terms in the fraction, you can simplify that. Now, if it was like this, if this was termed like this, and you had a 2 and a 4, these are the 2 and the 4s that you could simplify. But do you see the difference now? You can't just simplify terms that are connected by addition or subtraction symbols. So that would be the dunk, because you can't factor that anymore. All right, let's look at one more. What do we got? Oh, here's a good one. 6 over. No variables in this one. So this just has 2 radicals in the denominator. Not a big deal. Again, we're going to multiply by the conjugate. So that's the square root of 5 plus the square root of 3. And then that's what's going to be in the numerator. Now, this is, if you could get good at these, right? Do you see that the denominator here is just going to be 5 minus 3? Like, do you have to write out those middle terms? Like, you know they're going to cancel. Like, it's going to cancel every time. So could you just worry about doing square root of 5 times 5, square root of 5, which is 5, and then square root of 3 times square root of 3, which is negative 3 because of that negative sign? Like, if you get good at these, poof, you just know that's what's going to be in the denominator. Now you do the numerator. So 6 times the quantity, square root of 5 plus the square root of 3. And then to save me writing a line, you see that the denominator is 5 minus 3, right? Really, which is, that's a 2. So it's 6 over 2 or 3. So my final answer is 3 times the quantity, square root of 5 plus square root of 3. So also, if you're ever thinking, oh, well, that's all numbers, do you want me to evaluate that like on my calculator? The answer is no. I want you to leave it like that. You don't have to evaluate any of these numbers. Okay? So that would be the final answer. So do not eval numbers. And it's factored. Yeah, not too bad. All right, so that's rationalizing the denominator. You can do the same process for rationalizing the numerator. Same process. So let's look at an example. Now these ones, the book is setting you up. Does anyone have to take Math 107 after this? No? All right, so we won't spend too much time on this. I didn't see any hands over there? No Math 107s? All right. So this is an important thing for Math 107 because it has to do with the definition of a limit in calculus. This process is important. Okay. So there we go. But now that square root over there has got a binomial underneath there. But it doesn't change the fact of how to solve the problem. So what's our conjugate? Well, now we're just looking in the numerator. So it's the square root of y plus 9 and then plus 3 all over square root of y plus 9 plus 3. Okay, so we'll go ahead and do this. So we got to FOIL the numerator. But again, if you get good at these, you see that you're gonna do square root of y plus 9 times the square root of y plus 9. Is everyone okay with knowing that's going to be y plus 9, right? And then it's negative 3 times a positive 3 or a minus 9. I'm ignoring those middle terms because I know they're going to cancel. And then in the denominator, we have y times the quantity square root of y plus 9 plus 3. So what happens to those 9s? Right, the 9s go to 0. So you have y over y times the square root of y plus 9 plus 3. And what happens to those y's then? Right, you can cancel them out, so there's 1. So my final answer is 1 over the square root of y plus 9 plus 3. So instead of having the square root in the numerator, we now have it in the denominator. Okay? And again, since I don't know Math 107s, again, no Math 107s. All right. Again, but really, it's the same process. It's just doing for the numerator, not instead of the denominator. All right, folks, we've entered the last part. Is it the last part? It is. It's the last part of this section. And it's on rational exponents. Oh, boy. Okay, now, so let's say you had the square root of 2. Is it possible to rewrite that as an exponent? You've probably seen this at some point in your life. Or did you? Yeah. Yeah, so the square root of 2 is the same thing as 2 to the 1/2 power. So exponents and radicals are linked, right? They're essentially the same thing, and it's just a different way to express it. Now, generally speaking, if you had the square root of a, but let's not call it a square root, let's call it the nth root, that would be a to the 1 over n. So this is the big thing to remember. When you're changing them to exponents, whatever this is in the denominator of the fractional exponent, okay? Got to remember that, because sometimes you'll have something like this. How about this? The nth root of a to the m. What would that be in exponent form? Yep, so that's the thing. The n is always in the denominator, so it's m over n. Okay, so that would show up in something like this. What if I had, let's say this is the cube root of 2 squared. How can I write that as an exponent? Well, it would be the base is 2, and then it's 2 over 3, right? Okay. So the types of problems that we're going to see, and again, I'm not going to give you too many crazy ones. Okay. Let's just start with some simple ones. And again, I think the goal would be to, because you're going to be given these fractional exponents, and the first thing is to try to change them into radicals, because we know how to do radicals. I think they're probably easier than thinking about them in terms of exponents. So let's look at a real basic one. Say 9 over 25. But I'm going to raise it to the negative 3 halves. All right, so what's the first thing we would want to do? All right, let's just distribute that negative 3 halves exponent. So is everyone okay with this next step? It would be 9 to the negative 3 halves over 25 to the negative 3 halves. Because remember, when you're raising an exponent to an exponent, you multiply. And really, the exponents of 9 are 1. So that's why they just retain that negative 3 halves. Now, what do negative signs do as exponents? What's their function? Negative exponents do what? Like if I had x to the negative 2, how could I rewrite that? Wouldn't that be 1 over x squared? Right? Doesn't it flip where it is in the fraction? So here's all I'm going to do. I'm just going to put the 25 and make it a positive 3 halves in the numerator, and then a 9 to the positive 3 halves in the denominator. Okay? All right, now let's rewrite these as radicals. I'll put it down here just so I have room. So let's start with the numerator. What would that be? What type of radical is it? Square root or cubic root? Yeah. It's a square root, and inside of it I have 25 cubed. In the denominator, it's also a square root because the fraction has a 2 in the denominator as the exponent. And then it's 9 cubed. Now you could multiply out 25 cubed and 9 cubed, but then what you're going to have to do is factor it anyway. But here's a trick. Not really a trick, right? Do you remember when we did this with variables? I'll just put this as an aside. If we had like x cubed, remember how we changed that to the square root of x squared times the square root of x? Can we do that here with numbers? Yeah, because variables are just replacements for numbers. So this radical in the numerator becomes the square root of 25 squared times the square root of 25. Right? And then in the denominator, we do the same thing. The square root of 9 squared times the square root of 9. Now, are they all easily evaluatable? I may have just made that word up, but yeah. What's the square root of 25 squared? It's just 25, right? And the square root of 25? 5. The denominator, square root of 9 squared is 9, right? It's the square root of 81. And then the square root of 9 is 3. So what do we have? We have 5 times 125, which is, or 5 times 25, which is 125, and it's all over 27. All right? So we're kind of using all these rules, well, a lot of these rules that we learned in this section. All right, let me see which other one would be interesting. How about, oh, I like this one. Let's do this one. I'm going to do 2 of these. So I have 16x cubed raised to the 1/2 power. So let's go ahead and follow the same steps, and we're going to go ahead and, just as an example too, the 16 has a 1 here, okay? What do you do when you raise a power to a power? You multiply them. So it's 16, we're going to get 16 halves, and then x to the 3 halves. Everyone okay there? Now let's change them into square roots. 16 to the 1/2 is easy. That's the square root of 16. And then this is the square root of x cubed. So the square root of 16 is there, and then I can split up the x cubed to be square root of x squared times the square root of x. So my final answer will be 4x x square root of x. Yeah, and that's as crazy, I think, as I'm going to have you go with these. So they'll just be something like, because really it's just, I want to make sure people understand fractional exponents without giving you these crazy, because there's a lot of hard, difficult problems in P6, and that's not my goal, to make you stressed out. So here's what we got. That is the end of P6. Hallelujah. So here's the homework. So this is homework for P.6. Now, I'll tell you this now. I'm not going to have you hand this in Thursday, okay? But come with questions, and I'll go through a bunch of them at the beginning. That'll be good for the review. So that means you'll have 3 homeworks for that first exam. So if you've handed those in and there's never a problem, that means you get 6 points, right, on that first exam, which will be super helpful. Okay, so homework P6, and I'll leave the book up here if anyone would like to come up and take pictures of the problem. So, what am I looking at here? We're going to do 72 and 73 of the pages. So I have 9 through 17, and these will all be odd. $25. Stop it. I bumped a program. It's going to try to open like 1,000 things. 25 through 37. $46. I know it's an even, but it's a good problem. We can go over it to make sure you know the answer. 46, 47. 51 and 53. 63 to 69. 77 and 79. Yeah, and we'll do 85 to 91. Now that list looks big, but really it's not, right? So these are all odd, except number 46. So it's not too bad. So what we'll do is we'll go over that first thing on Thursday. So this is perfect. You got about 5 minutes. And again, if the first rows can come up, go ahead and clean their seats. And you know the drill by now. And we'll be good to go.